Google unveiled two breakthroughs that could reshape the entire future of artificial intelligence. One team has discovered a strange yet brilliant new way to teach smaller AIs how to think, using a hybrid training method that fuses two systems never meant to coexist. At the same time, another Google research group quietly built an AI scientist, one capable of solving a decade-old biological mystery that baffled human experts for years, and it cracked the code in just days. Let's start with the first discovery, because it might be the smartest training trick Google has ever pulled off. A collaboration between Google Cloud AI Research and UCLA has introduced something called Supervised Reinforcement Learning, or SRL. The name alone sounds odd, because supervised and reinforcement learning usually sit on opposite sides of the AI spectrum. In supervised learning, a model is given the correct answers up front and learns by example. In reinforcement learning, it has to explore, make mistakes, and earn rewards for correct behavior. But Google's twist is ingenious. SRL gives the model the answers, yet still forces it to earn them step by step through rewards. It's like handing a student the solution sheet, but still requiring them to show all their work to prove they understand it. It sounds contradictory, but it works beautifully. Here's the problem Google wanted to solve. Small models often collapse when faced with complex reasoning tasks. Even if you feed them perfect examples, they tend to imitate patterns instead of truly learning. Long sequences, tiny datasets, the result? Their accuracy drops below the base model. So, researchers asked, how can a small model reason instead of repeat? Their answer, SRL. Instead of punishing errors through a loss function, SRL injects supervision into the reward channel. Every expert solution is broken into tiny steps, called expert trajectories. At each step, the model generates its reasoning privately, wrapped inside special think tags, like a digital notepad, and produces a single action. That action is then compared to the expert step using a similarity score, and the model gets immediate feedback. The result? Dense rewards at every stage, even when the final answer is wrong. This means the AI learns which decisions actually matter, without simply copying the teacher's text. And the results are staggering. Across tests, using the same datasets and parameters, SRL-trained models outperformed their baselines by huge margins. When followed by another reinforcement phase called RLVR, the performance exploded, reaching the highest open-source benchmark scores recorded so far. But this isn't just about math. SRL also revolutionized code reasoning. When tested on complex software engineering problems, the SRL-trained model nearly doubled its accuracy compared to standard fine-tuning, all while using small datasets and minimal compute power. In essence, SRL redefines reasoning as decision-making, not prediction. Each action the AI takes is evaluated instantly, letting it master logic in tiny, learnable increments. Compared to traditional methods, it's a night-and-day improvement. No overfitting, no reward collapse, and no massive infrastructure required. Google has effectively taught a 7 billion parameter model to think with precision. Instead of just scaling bigger networks, they're building smarter, more self-aware ones. Tiny models that behave like heavyweight thinkers. That's a paradigm shift that could ripple across the entire AI landscape. But while one Google team was teaching machines how to reason, another was teaching them how to do science. Over at DeepMind, researchers built what they call the AI Co-Scientist, an autonomous research system capable of designing experiments, analyzing data, and forming hypotheses. It's powered by Gemini 2.0, but instead of a single model, it's a team of AI agents, each with a distinct scientific role. There's a generation agent that proposes new ideas, a reflection agent that reviews and critiques them, a ranking agent that scores them using an ELO-style tournament, an evolution agent that merges or mutates the best ideas, and finally, a meta-review agent that monitors everything, continuously improving the entire system. Humans still set the goals, but the heavy reasoning and exploration are done by this swarm of AIs. Their first big challenge? Finding new treatments for liver fibrosis, a deadly disease that causes scarring of the liver and has resisted effective drug discovery for decades. The AI was tasked with exploring epigenomic mechanisms, the chemical processes that regulate genes without altering DNA. It was given a single detailed prompt describing the problem, and then left to think. Within days, it analyzed thousands of scientific papers and proposed 3 potential drug candidates: HDAC inhibitors, DNMT1 inhibitors, and BRD4 inhibitors, along with detailed testing protocols. Researchers grew miniature human livers from stem cells to validate the results. 2 of the AIs suggested compounds worked flawlessly, reducing fibrosis fibrosis, and even promoting healthy liver regeneration. One of them, vorinostat, is already FDA approved for cancer. The AI repurposed it as a liver treatment, something nearly 200,000 published studies had overlooked. Out of all that research, only 2 papers had even tested the idea. Yet the AI found the connection instantly, and in side-by-side comparisons, its discoveries outperformed human-selected drug targets. That alone could have made headlines. But the same system went further, solving a completely different biological puzzle that had stumped scientists for over a decade. Working with Imperial College London, the AI investigated how certain bacterial DNA elements, known as capsid-forming phage-inducible chromosomal islands, managed to jump between species, despite viruses usually being species-specific. Given only pre-discovery data, the AI generated 5 possible explanations. Its top hypothesis: these genetic elements hijack virus tails from other species, a process scientists later named tail piracy. That was the exact mechanism human researchers spent 10 years uncovering. The AI got there in days. When tested against other top AI models, none came close to reproducing that reasoning. Gemini 2.0's multi-agent design was the only one capable of connecting the dots. Dr. Gary Peltz of Stanford called the speed unreal, noting his lab now uses the system for genetic research and drug repurposing, and believes AI scientists like this could soon revolutionize real-world medicine. We're only scratching the surface of what AI can do, so if you want to stay ahead of the curve, don't forget to like this video, subscribe, and turn on notifications, because the next discovery might just redefine everything we know.